All right. So welcome back. It's been 2 weeks. Nice to see you guys all again. Um, I don't know if you remember from 2 weeks ago, but there was a lecture on sorting. And we never did the recitation on sorting, even though the other group did. So this recitation, we're going to do the sorting really quickly, and then we're going to go to amortized analysis, okay? So bear with me while I run ahead with this, because technically in the other groups I had to teach some of the lecture. So here it should be fairly quickly. I'll skip over the stuff we don't have to go over. So let's do this. First, this is very important. Definitions in sorting. First, our input are elements. Let's say an ID or a card or information on students, and every element has a couple of fields. It's very important for the homework too.
Yes.
You can't just take the number and just say, oh, here's the number, I put it in the right spot. No, there could be other elements with it. One of those fields is called the key, and that's the field that we sort according to. Let's say for their ID numbers or their name or their last name, but there's one field that's called the key. And whenever we order the array, the order between two different keys is decided according to the order relation, right? The order relation in this case is always going to be for numbers, it's always greater equal or smaller equal. But for words and for other objects, you need to define a new ordered relation. And if there's also two elements, I can't believe no one asked me this, but if there's two elements with the same exact key, then in the definition of a regular order, in a regular sorting, then they just have to be together. They don't have to be in the correct order. They just have to be in together. So if I have this, let's say 2, 1, 2, 3. When I order this, I want the twos, even though they're the same key, I want them to be together. So therefore the sorting would look something like this, but I don't care which order the twos are. Okay, now that we have that, here's some sortings that we learned. We have insertion sort, bubble sort. We'll go through them really quickly. First, insertion sort. We always, at every iteration, at every ith iteration, we check that the prefix from 0 to I is ordered. So for this example, we start on the first iteration, which is 2. It's obviously ordered because it's only one element. And then the next one, we have to insert the next element. So we have 2, this one's ordered. We have to insert 1. So we look we search where to insert it, and then we insert it. And then we do the next element, it's 2, so we insert it afterwards. And then 3, we insert it afterwards. So at each iteration, we add the next element. Okay, and the runtime is O of n squared, because each time we have to check the whole prefix that we already have. So it would be 1, and then you have to check 2 operations and 3 operations, 4, 5 until n, which we know is O of n squared. Bubble sort, you might remember this from Intro to Computer Science, but we go through the whole array, and at each iteration, when we go through the whole array, we compare the 2 elements. And if they're in the wrong order, we switch them. Then we go to the next one and we switch them. We go to the next one and we switch them. So let's say for this, let's just do one iteration of this. We have these 2, which first we have to switch them because 1 is less than 2. And then we have these 2, we don't have to switch them. And then these 2, we also don't have to switch them, so we're done. And now you may remember this from intro, but at each iteration, we basically move the biggest element to the end. That's what we do at every iteration. In this case, there's only really one iteration. Hey, Sammy. In this case, we only did one iteration, but technically you could do an iteration if you keep on having to do. So what is the what? How many iterations?
No, what is
The runtime? The runtime is also n squared. It's also n squared because if you think about it, at every iteration we're doing n swaps and checks. And we have to do this at most n times. So n times n O of n squared. And also we stop the second we don't do any switches. Like for this case, right? we stopped once we did this, and then if we go over it again, we have to do any switches. So it's ordered, therefore we can stop. Okay. This is, once again, the translation is selection sort. Selection sort is very similar to insert sort, just that every iteration we check that the smallest elements are ordered in the beginning. So in each iteration, we just take the minimum of the remaining elements. So in the first iteration, we take 1 because it's the minimum. And then from the rest of them, we take the next minimum, which is 2. And then the next iteration, we take the next minimum, which is still 2. And then we take the final minimum, which is 3. So at every iteration, we're taking the minimum from the remaining elements and putting it in the beginning. And this also takes O of n squared, because each time we have to find the minimum, which takes n, and then n minus 1, and n minus 2. And we do n of those iterations. So this is also O of n squared. Okay, quick sort. We learned this in divide and conquer, and also I hope you learned this also in the lecture. But the way that this works is you choose a pivot, either the first one or a random pivot, and you partition the whole array around that pivot. So let's say we choose, this is a bad example, but let's say we have 5 here. Let's say we choose 3 as our pivot. So 3 is going to be our pivot. And the rest of the elements we decide are they going to be before or after. So we have 2, 1, 2, and we have, just 5 here. And then on each half, we operate recursively. Again, exactly. So here we have 1 element, so we're done. Return sorted. Here we choose another partition. So we choose 2, and then we'll sort it again. Each one will come back sorted. And then this whole sub array will come back sorted. And then this whole array is already sorted. This is, in the worst case, it's O of n squared. Why is it worst case O of n squared?
Most of the amount of pivots I need to choose. And like if it's
worst case, we keep on choosing a bad pivot. What's a bad pivot? The smallest element or the largest element. Because then we pivot, and all the elements, if we chose 5 as a pivot, all the elements would be on one side. Then we have to do n recursive calls, because each time we subtract it by 1, it would be O of n squared. But I don't know if you proved this in the lecture, but in expectation, it's n log n. That's why it is a good sort.
wait, what's the difference between the expectation and the
In the worst case,
expectation is just the average?
expectation is, it's not exactly the average, it's what we can expect. If we run the algorithm like a bunch of times, like what I guess it's similar to average, but it's not exactly. No, that's something else. That's amortized analysis.
2 different things.
That's amortized analysis. If you would come on time, then you would know that we're going into that after.
No, I see what you
Okay.
wait, so there's 3 different things.
There's 3 different things. There's regular worst case, there's expected, there's amortized analysis, and also in hashing you have a 4th thing, which is in high probability.
Yeah,
right? High probability is the 4th one.
And we need to know how to calculate with that.
Yes. Okay. Merge sort. Merge sort, you guys all know from divide and conquer. We divide the array into 2 halves. We recursively call on each half, and each half of the array comes back sorted. And then we have 2 sorted arrays, and we have to merge between them, which we know how to do in O of 1 by going over with 2 pointers. We went over it in that recitation, but if you have 2 sorted arrays, you just go through element by element and just always take the minimum between them and continue onward. This is, in worst case, it's n log n, so it's a bit better in certain cases. Okay. And also, it's very important that you also know the differences between all these, because they all work a little bit differently. So it is important that you know all them, because I could ask you on any of them on a test. AVL sort is just what it sounds. We insert n elements into an AVL tree. Each insertion costs us log n, so therefore it would be O of n log n. And then we just do in order traversal. We already proved it, since it's a binary search tree, and in order traversal, prints them in sorted order. So therefore, the total time would be O of n log n. Heap sort is not on the slides, but heap sort is basically the same idea. Let's build a heap out of our n elements, which we know we can do in O of n, right? We saw the algorithm that does an O of n, building a heap. And then once you have a heap, you extract the minimum n times. Extract minimum takes log n. So for in total, it's also n log n. Okay, now, stable sorting, right? It's called stable sorting. Okay, it's called stable sorting. Stable sorting is basically what happens when we have two keys that are identical. We have two identical keys. We want to preserve the original order between them. So here we have 3 5s, but we want to preserve, once we sort it, the original order. So this 5 would be last, then this 5 would be second to last, and this 5 would be third to last. Okay? Gotta see an example. We want to preserve regular sorting. We don't care about the order between the same keys. If we have identical keys, I don't care which 5 you put first. That was in the definition from the beginning. But now I'm saying if you want the stable sort, the definition is a sort that keeps the original order between identical keys. So therefore, this 5 would be last. This 5 would be second to last because its index is smaller. Between the 3 5s, which are here, the original order of them is preserved.
So you have to sort it.
So we have to, that's one way of thinking about it, but there are some sorting algorithms that we learn that already do this automatically, and we don't have to touch anything. So not all the sortings that we learn are stable. That, for example, quicksort is not stable. Why is quicksort not stable?
Swapping.
The swapping?
Yeah.
Yeah, the swapping.
You mean sort.
What?
Yeah.
Mean sort. Doesn't mean test.
No, they mean sort. Also in the other sense.
Mune is a draft also. It's draft or
It's sorting.
here it's sort. Don't ever write like draft or don't take it as always in this course. It's always you can sorting. Okay, so you see that all the identical keys preserve the same order in the original array. Now in quicksort, let's say you can even take an example for it to be a little bit more understood. Really, you have to go into how the partition works to fully understand why it's not stable sort. But let's say if you take this 5, the middle 5 as the pivot.
Yeah.
Then I have to put the 5s on one side or the other side, right? So if I put both the 5s on this side, if they're equal, I put it on that side, then this 5 won't be in the original order. If I put them both on the first side, then this 5 won't be in the correct order. The stable sort is when you have a sort is just sort the elements such that each key, like if there's two different keys, they have the original order. Not the original, they have an order between them, right? So 0 and 2, we know 2 is bigger than 0, so 2 will be after 0. But what happens if you have two keys that are the same, right? So in a normal sorting, we don't care. As long as they're together, we don't care which order you give them to me. As long as they're together. But in this case, in stable sort, we want to preserve the original order between them.
Why would we ever want to do?
Let's say
I can give you an example.
let's say we have, let's say we keep track of people who come into the class, right? So technically you came late and then you went to the bathroom and you came back. So I have two separate like timestamps of when you entered the class.
Right.
And if I'm sorting it by your ID, it's the same ID, right?
Yeah.
But I would want it in the original order, right? Because I'd want to see like what's the order of what you when you left and entered the class.
Okay.
It's useful in many cases. You'll see also why it is useful, and we'll get to there.
Let's see, sort. And a sort that doesn't compare every two values.
By worker mean runtime.
Yeah.
So there are sortings that are just stable by definition, but ones that aren't stable by definition, we're going to get to them. We can turn them into stable without increasing the asymptotic time by adding just a constant amount of actions, operations. So here's a summary of what we've done until now. AI really helped me make this. The stable, these are what's stable and what's not stable. Runtime, best, average, and worst. It's on the.
It's like a
Oh, I didn't upload it. Did I upload it for you guys? I didn't upload the presentation, huh? Yeah, I uploaded it to the Hebrew ones, but.
Oh, also,
Yes.
if you want to make a
Oh, I did upload it. It's on. It's on. I uploaded it a long time ago. Yes.
if you want to do a solid, whenever you have time before the test, upload like for every structure we learn, like dictionary, list, whatever.
You can make that yourself.
Yeah, but like which ones are legal and which ones are not?
You can do it yourself. If I have time, I'll get to it. Okay.
Sure.
It was an idea of mine, like without you asking, so I hope I'll get to it, but I can't promise
Do
anything.
you need to, sorting stable,
The what?
how to prove it?
To prove the stable sorting.
Yeah, to prove why is it stable, they need to know.
So the sorting algorithms that we have, you can just use as we know that they're stable because we showed you in the lecture. We showed you that they're stable. If you invent a new sort, then yeah, you'd have to prove it's stable.
How do they do that? Like,
We'll get.
or it's enough,
What?
or it would be enough.
No. I mean, I can't promise it's not going to be on the test. It probably won't be on the test to prove that something is stable. But if you do, what you have to do is with induction on the
Two
what?
singular ones that
On, yeah, induction on the elements, exactly. And then just showing that it preserves the order. According to the algorithm. Okay, so now describe a method of turning any algorithm, even if it's not stable, to stable. Kind of connects to what we did before this, but
After we sorted, not stable,
yeah.
we started to sort it into stable.
What do you mean after we start? We
had
sorted the
the
first time and it's not stable.
Yes,
And now what do you do?
not the indexing
Okay, yeah.
before, what was before.
Yeah, the index, you say the index,
So
and you sort according to that.
yes.
Exactly. Sort of. We're gonna do it a little bit more formally, because we don't want to sort twice. So instead, what we're gonna do is we're gonna change the keys to be pairs.
Yes.
The keys are now gonna be pairs of the actual key and also the index. And we're gonna sort by the original key. And if there are two identical keys, we'll sort by the index. Okay? So therefore, we need another O of n. Space is an important note, even though we just added a field, it's O of 1. But we added a field to every single key, therefore it's an additional O of n space. And the comparison still takes O of 1, because the one comparison now, worst case, we have two comparisons. If they're the same, we compare the index. So it's still O of 1 per comparison, and we didn't add anything to the runtime. Questions on this? No? Okay. All right, so you saw in the lecture, it's not a spoiler, it's a reminder. You saw in the lecture that any algorithm that is based on comparisons runs in at least omega of n log n time.
Oh, you uploaded this.
What?
You uploaded the presentation. I saw.
Yeah, I did upload it. Yeah, I uploaded it. Okay, so it's at least n log n time, right? We proved it in the lecture with decision trees. And what is a sorting algorithm that's based on comparisons? This is really important. What is that algorithm? It's when you don't have any other additional information, right? You don't have any additional information. You have to compare between. That's your only method of sorting it, is by comparing. Therefore, those will be at least n log n. But we'll see, and you saw also in the lecture, that there are sortings that have additional information, specifically count sort and radix sort, that have a limit on the range. And then with that extra information, you can reduce the runtime less than this. But if you're given no additional information, this is the best you can do. So now there's a lot of these questions on tests. Either prove or disprove that some abstract definition of a data structure either can exist or it can't exist. If it can exist, you have to show me how to implement it. If it doesn't exist, you have to prove that it can't exist. So
Like
now,
a contradiction or?
exactly. So we're going to assume for the sake of contradiction that this does exist. Then we're going to use it as like a black box. And we'll get to some sort of contradiction to something that we know. So in this case, we're going to get to a contradiction with the lower bound of comparison sorts. So somehow we're going to use this to sort with no additional information in less than n log n.
Well,
Okay.
because we can sort in less than n log n, we need no extra information. This is a contradiction of
It's a contradiction of the lower bound because it's a contradiction because we know that there's a lower bound. We proved it. And now we got less than the lower bound, and therefore this can exist. Okay. So let's see how we do that. Assume for the sake of contradiction that something like this exists, and then we'll show an algorithm that sorts our n elements. We're going to build that data structure with the n elements. As long as the data structure is not empty, we'll just remove the minimum and print it and how much time the runtime is log n. Yeah. This is basically like heap sort. It's very similar to heap, right? Heap, we can build an O of n, and we can take out the minimum in log n.
So
But
it's
here-
n log n. That's
Here, exactly. Here, what we're doing is we're doing O of n, and then we're doing n times a log n operation. So therefore, we'll receive a sort of this of these n elements, but the runtime is n log n, which is less than n log n contradiction to the lower bound on comparison sorts. Okay, so we assume for the sake of contradiction that data structure exists, and we're going to use it to sort our n elements, and that's an n log n. That's a contradiction because we don't have any additional information, therefore you have to use comparison sorting algorithm.
What's something below?
The below means that
it's way bigger.
this is way bigger than this. It can't be right if it was big O. Sorry, not big O. If it was like theta or something, it would be like equal. If it was big O,
It would be an
if it was big O, it could be an upper bound, but it could be equal. Right? So little o is strictly smaller. Exactly. Okay. Other types of sorts you guys saw us in lecture, so I'm going to go through them a little bit quickly. Like we said, comparison sorts is when we have no additional information, but sometimes we have additional information, therefore we don't have to do comparisons, and we can do it in less than n log n time. First is the count sort. Given an array of A with n elements, such that all the elements in A are within the range of 0 to R, we have to sort this, right? Every number is an ID, and it has other information, right? So we can't just count the amount of numbers here. So you already saw this in the lecture. We're going to first, this is how the algorithm is going to work, the count sort. We're going to make a new array C, the size of the range, so therefore R. And we're going to count the amount of appearances that each element has in the original array. So we're going to loop through the original array, and every time we get to an appearance, we'll go to that index and add 1. So here we start as a 2, so we'll go to the index, the second index, and add 1. And then for 3, we'll go to the third index and add 1. So, and so on and so forth for 0, for 5, and once we get to the end, then we have the total amount of appearances of these elements in the original array. Now, pay attention that this, we can't just use this to sort we can't just stop here. Because technically I know now that there's 2 zeros, and then we'll put 2 2s, and then 2 3s, and then 3 5s. But remember that there's additional fields. You can't just, it's not only a number, it's a number and additional fields. Okay? So you can't just take this, we're gonna have to do some more things. So first the question, how many appearances of 3 do we have in the original array? 2. You go to the index 3, and we have 2 appearances. Where are they in the result array? We do know.
We know it's
Where are they going to be?
6.
Not each one, but where are they going to be?
6.
Close. It starts from zero index. So 4 and 5.
0 indexing is down for 4 and 5.
4 and 5, right? Why? Because the first 2 the first two zeros will be in 0 and 1, and then the 2's will be 2 and 3, and then the 3's will be in 4 and 5. Now we want to be able to calculate the placement of each number very quickly. I don't want to have to sum all of the previous numbers. So what I'm going to do is I'm going to already just sum it ahead of time. So each index will not only be the amount of appearances that it has, it's the amount of appearances that it has and everything less than it. So we're just going to sum it, and how we're going to do that is we're just going to add every cell, we're going to add its value plus the value before it. So we're going to have 2, the next one will be 2, the next one will be 4, and so on and so forth. So now, when I ask you, what? This is another array, or you can even go through the original C array and just operate on it. But here they just, for drawing, I think they just did it in a new array. And now once we have this, we can go in reverse order from the original
Yes.
and insert this into the place that this is basically tells us where to put it. You did it in the lecture. I'm just going over it now. So here in the lecture was actually
talked about
for this specific with me. When?
The last
No, actually,
Last time was hashing.
just in Hershey?
Just not hashing.
So this about it.
No, he did in the last like 2 minutes. He went like for crazy
Oh, in
and
the
did
lecture.
these two.
The
Yeah, in
lecture.
the lecture. You're right. Like really, really,
He
really
told me he
fast.
did this in the lecture.
So I get fast.
Because in the other recitation I had to, I taught this like in the lecture. Anyways, so back to our algorithm. Now we're in the place where we want to go from the end to the beginning. And
I
we
just
want
did this as a homework. I didn't know we were going to talk
Yeah.
about this.
exactly with the prerequisite. 5, we're gonna insert it wherever this points. This basically telling us where we're gonna put that same element, right? So we're gonna go to the index 5 in our count, and there's 9. Here they did it by 9, but in the lecture you saw it was 8. Here we're gonna do this number minus 1 is gonna be the index of it in the new output array. So 5 is now gonna go to the 8th place. We're going to do it minus 1, and then we're going to subtract 1 from this original, from this cell, right? So we can subtract, and then we put it in that place, right? So now 2, where's 2 going to go? Who can tell me?
Or 3 in this case, because
3,
one,
exactly. So we go to 2, we subtract 1, and then we put it into the index. Okay? And now we don't just put the number. Remember, 2 also has additional fields, right? We
Yes.
put additional fields, 2. And now 0, where does 0 go?
That's 1.
In the first spot, we take 1 off of 0,
The one.
and we insert it into 1. Exactly. Now where does 5 go?
7.
7. Where does 3 go? 5. Go to this, minus 1. All right, and so on and so forth till we get to the end, and now we have our sorted array.
Nice.
And it preserves the additional fields. And we'll see it's also stable sort.
Yes.
Yeah? Okay. First, summary of all the different stages. First, we have to count the amount of appearances in the original array and put them into C, into our auxiliary array. And then we have to calculate the prefixes of it, not just every I, how many times it appears, but every I and less than I. How many appearances are less or equal than I. And then we go from the end to the beginning and we put it into the array according to that same helper array. Okay, so the runtime, first counting it, we go through the original array, let's go with n, and then we go through the C array, the helper array, and that is the size of R, the range, because we have to have the all the elements of the range, so it's just the size of the range, and then we copy all the elements to the new array. Total runtime is n plus R. This is the pseudocode. In the lecture, you went through the pseudocode line by line, so I'm not going to do that now. Also, note that if we're sorting numbers from the range of R, if R is equals C times some constant times N, then our total runtime will be O of N, right?
Yes.
If R is some C times N, if our range is something that is dependent on N,
So C to
then
it's
it's
to
N
CN.
plus, exactly, it's C plus 1 times N, which is just constant times N, it's O of N.
Which all can be bigger than n.
R can be bigger than N. If let's say N is 100, but I gave you a number within one of those 100 elements, 1,000,000. So it wouldn't be worth it to use this, because that's like N to the third power. You don't want N to the third power sorting, that's not great. So it's, in certain cases, it's very useful. In certain cases, it doesn't help us at all.
Fantastic.
All right, so count sort is stable. Every 2 elements with the same key, keep the original order after the sorting. Okay, radic sort. I'm gonna have to go through this one quickly because we have a lot to do afterwards. And I was gonna record this for you guys, but I thought that might be better just to do it quickly now, so then I don't waste another hour of your life. So let's do this.
Hey, don't be like that. We can put it at times 2. You're just wasting half an hour.
That's true. Okay, so now radic sort is very similar to count sort, but now instead of a range, we're given a range. Instead of until R, now it's given until R to the power of some D. So for example, sorting numbers in base 10 until 1,000,000. Okay, so therefore R would be 10, because each digit is from 0 to 9. So there's 10 elements per R, but we have 7 digits, or in this case, 6 digits if we do it until 999,999. We'll see an example and it'll be a lot clearer. So first, the idea is just sort per digit, right? So how it's gonna work. For every I between 1 and D, we're gonna sort the array for that digit in a stable sort, right? So we're gonna first do it on ones. Let's say this is our array of numbers we want to sort, right? So 2,871, we want to sort all of these. So we start by the ones. We're going to sort them.
This is a 2D array.
It's not a 2D array, it's a 1D array of numbers, but it's just for the animation. It's divided up into cells.
Yeah.
Think of it as just a number 2,871, and then 4,591.
So we're basically picking every fourth number to sort in this case.
No,
Not exactly. We're sorting it by digit. We're sorting it by the ones digit, and then by the tens digit, and then by the 100 digit, and then by the 1,000 digit.
This I remember we clearly did it in the.
We did this in the lecture, but I'll just go over it again. So first we sort by the ones digit.
Probably.
So I could explain not having this.
First we sort by the ones digit. So as you can see, all the ones that I've sorted, and also we're using a stable sort for each digit. So therefore the original order, 2,000 is still before 4,000, even though we sorted them by the ones. Even though these are identical keys, it still preserves the original order. And now we're going to sort by the tens. You can see that so from 0 to 9, right? We're sorting by the tens, but preserving the order from before because it's a stable sort. So therefore, if we have 2 elements with the same number, let's say 7 and 7, we preserve the original order. This number is before this number. Okay. And now we're going to sort by the thousands, by the hundreds, and then by the thousands, and we have our sorted array. Now, claim the radic sort truly sorts our array. First question's on radic sort. I'm running through it, but that's because I wanted to do half-half.
But how is it sorted?
Because
How is
you're
it sorted?
sorting.
You have 1,000, right? It's the smallest. Then 2,000 is a little bit bigger. 2,800 is a little bit bigger. 3,000 a bit bigger, right? These are all numbers.
Oh,
Ignore the lines
it's
here.
a single input.
It's a single input. The 2,871 is a single element. And we're sorting it, we're dividing it up into digits to sort by.
Okay.
So we're sorting it first by the ones, then by the tens, then by the
You're moving
hundred.
the whole numbers, not just the line you're sorting.
Okay?
And that works, that preserves the number.
Because
It preserves the number because we're using on each digit a stable sort, which preserves if the key is the same, then it preserves the original order. And what's the original order? It's the order of the other digits that we already sorted. So now let's prove that it truly sorts. First, the proof is let x and y be two elements from our array, and they have digits from 1 to these are just the different digits, but they're just x and y are two different elements. Let's assume, without loss of generality, that x is smaller than 1, because otherwise it's symmetric. It doesn't really matter. Let's denote I as the first place that they differ. That's it. Let's take an example just so it's a little bit clearer. Let's say we have 1,004,000, 1,000,000, and 5,000. So this is our, this is our x, and this is our y. Okay. So let's denote I, the greatest index that they're different. What's the greatest index that they're different? This one, right? So this will be I. And now we know that x in the place of I is smaller than y in the place of I, because x is smaller than y. We know that the rest of them are equal. The rest of the digits are equal. So therefore, xi is smaller than yi. In the ith iteration, we're promised that 4 is before 5, because that's how the sorting that we used works. So we're promised that x is before y, and therefore in the future sortings, because of the sort that we used is in fact stable, therefore it will keep this original order throughout the whole every 2 digits that are the same key. So therefore it'll preserve the original order, but that step of preserving for the identical keys, you have to prove with induction. Because you can't just say that it keeps the original order. You say you do with induction on n, it's very simple. You assume until n, and you prove for n. Right? And basically if it's kept until now, on this iteration, when we check it with the stable sort, it's still stable sort and it'll keep the original order. That's it. We're done with the proof of induction. Now also question, how are we going to sort each digit? With count sort that we learned a couple minutes ago, because we know the range is from 0 to 9. Right? So it's very simple to use count sort. Count sort is also stable. Therefore, it's very good for us. Now, radic sort, the runtime. For every one of the digits, we perform count sort in time of O of n plus r. There are d different digits, d columns. Therefore, total, we times this by d and we get this runtime. Okay? We need O of n plus r space because same as count sort, we need an array of 9 elements. Let's do. And note that if r equals n, if our range equals n, we will get that this whole thing, n plus r, is just 2n, which is O of n, and we'll get a runtime of n times d instead of d times n plus r.
D is the amount of digits.
D is the amount of digits, r is the range of each digit. Also, if r is constant, it doesn't change the runtime at all. If r is constant or something, a constant times n, it doesn't matter because both of them are going to be O of n times d. Whether or not r is constant or something constant times d. All right, we finished with the sortings. Mazel tov. Using select, we're going to do this question, and then I don't have to skip. There are some questions from test on here. You're welcome to go through them. I'm just not going to have enough time to go through them. Okay, so now we saw in the lecture, it's very important. This part is really important because in the lecture, select is all over the place. You do the proof, you're like, what the heck is going on? But we're going to use it as a black box. Okay. The input of select is an array A of n different elements and a number, natural number k. And the output is the kth element in its size, right? So if this is our array, let's say, actually it's a terrible example. Here we have this this array. So if I want the k equals the second element in its size, that would be 2. And so what select does is it also gives me what that element is. And also it divides the array up such that all elements smaller than 2 will be on the left side, and all the elements that are greater than 2 are on the right side. So the k equals 3. I think it's just a little bit more it's a little clearer here. So 3 would be our element that we look for. And then 2 and 1 would be on this side. And 5 and 7 would be on this side, but they're not necessarily sorted. So this is just take it as a black box. Forget we do it in the lecture. This is how it works. You get an input, you get an output. I highly recommend watching a video. Adval is a great video. Or
I sent it in the Hebrew one.
send it to them too. She has a great video, or you watch go over the lecture, but because it is important to know. But now we're just gonna use it as a black box. That's a little bit of a reminder. You divide it into 5s. You sort each one. You find the median, partition, trauma.
Yes.
Okay, question, and then we're gonna go on to the next recitation. So, given n points on number
line.
let's call this a number line.
Yeah.
Okay, on a number line and natural number k. Propose an algorithm, the most with the best runtime that finds the k points that are closest to the median of all the points. So let's see an example for that. Let's say these are our points. They're given to us. Remember, they're also not sorted here. So we can't assume that they're sorted, but let's say we have them like this. We have to find the median and find the k points that are closest to the median. So we want to find the 4 points that are closest to the median. So it's the median itself. It's this point. It's the closest to here. Second closest. And then not this one, but this one is the third closest.
K neighbors.
What?
K neighbors.
Sort of. A little bit different though. All right, so we need to do this. Now, when we approach questions like these, usually I give you time to think about it, but I'm going to give you a little bit of help. You want to break up the steps. We first need to find the median, right? That's the first step. You need to know the median in order to know everything else. How do we find the median?
Select.
Select. Just plug it into select, right? Select receives the number k. Let's just insert k equals n divided by 2.
The median. Okay. Yeah.
We want the median. The median is the n divided by 2th in its size. It's the one in the exact middle. We can't just go through this and find, because this isn't give us sorted, right? It's n points that aren't sorted. So we have to, in a non-sorted array, find the median. How do we do that? Let's select. Okay, so that's our first step. Second step, once we find this, we need to know the distances. Right now it's like very visual and pretty. But when you get n random points, it's not so pretty. So how are we going to find the closest ones? We're going to create an array of distances, another array of distances of each point from the median. Now that we know the median, we'll take each point, which is a number, subtract it from the median, and do that in absolute value. Get the distance.
Mhm.
And then for each point, we have the distance.
Yeah.
And now once we have that distance array, we want to find the k closest points to it.
We're going to the select again.
So we do the select again, because we want the k smallest from that array, because those are the k dots, k points with the smallest distance. Okay? And then once we find that k, let's say it's 3, To the right of it are all the elements that are smaller than it. And we just return these, and that's it. We're done. Okay, so let's just see it quickly. First, we'll find the median. For every element, we'll calculate the distance from the median, right? Which is just the absolute value of the difference. And then in that array of distances, we'll finally select the element that is kth in its size. And remember, this is distances. Now it's distances from the median. So the kth would be the kth in its distance, which we will include it and everything smaller than it to be in our output. And we'll return them. Any questions on this?
How we find the distances, the K.
With select.
Select provides like an amount, not a specific number, right? That's how it works.
What do you mean an amount?
Because like you want the k, not like it's not a select equals to k. It's just the amount k. We want like the k, the number, because like if you would need to provide an amount, like what's the distance, you wouldn't know. You just need to provide an amount of points.
No, we need to provide the points themselves.
Yeah, I know what I mean.
Okay.
It's like the k is not like the amount you're looking for. K is not like the distance you're looking for. K is like the amount of points that are smaller than it. Because if you have to provide the distance, you can't do it.
Why not?
Because you don't know what the k smallest distance is.
Why not go to the array and check?
Yeah, but you need to sort it to know. Like
Are you
what
sure?
you're trying
I'm not sure you're right.
what you're trying to find is the k points that are closest to that median.
So I have my array and I do select on the
Yeah, and select
It
and
returns
for select you input the amount of points you want, not like the distance you want, because you don't know what.
it's not the distance, you're right. It gives me the element that is kth in its size. So here it's if I want the third in its size, it'll return this element,
Yeah, so
which is the distance.
so what you provide select is the amount of points, not the distance that is like from there, because like you don't know distance.
The distance I operate no, I
No,
think
no.
we'll talk about this afterwards, okay? Come to me afterwards. Let me get a question.
Yeah, select is a function.
Yes.
Okay.
It's a recursive function, but it's a function.
When did we see it?
2 classes ago.
2-3 classes ago.
Well, I haven't really used it.
No, it's okay. This one was kind of hard. It's a really hard algorithm, and we only used it a little bit later. But if you use it as a black box, like that's how it works.
And now we use it as a black box in the test.
Yeah, for sure.
Oh,
Unless they ask you, I've seen a test question where they ask, right? We saw that that it divides into fives. So there's a test question where it divided into 7, right? And show me the runtime. So you do have to know how it works, but more importantly is how to use it, because that's more often was the case. Okay, now let's go to the next one. There are more awesome questions here. I took this from a test question. Very cool,
Yeah, very.
but we are running out of time. If we have time, we'll go back to it.
I didn't have a select one. I have a like how is it called again? Quick sort algorithm.
Okay.
I think this is what I said, but quicksort uses partition,
Mhm.
and then the moment you get partition, it's quite easier to get select, because select is like partition is a smart, I don't know how to say it, starting point.
Mm-hmm.
So like it helps, but it
So using quicksort helps with the select.
yeah, because you partition is kind of like most of it what
Yeah.
you do, and select what you do is just you find a smart one,
Mm-hmm. Yeah.
smart like pivot point,
Yeah.
and then uses partitions. So
So you're
it
saying,
builds on this.
yeah.
But we still send a video. And
You send the video. It's a great.
because there is no select algorithm. There's only quick select also.
Quick select.
Yes.
That's the algorithm.
This is how it's called on YouTube.
Okay.
I will look it up.
So
I will send
we'll
this
call
one
it-
'cause it's really
We'll call it just select algorithm. But yeah, watch the video, Sammy. If you or everyone else,
It really helps.
watch the video because if you don't remember it, it is important. Okay, so now to amortize. Now this you should be more familiar with because it was just yesterday. Who can tell me what amortized analysis is?
Don't look at us, we want in the lecture.
What is amortized
is it?
analysis? What is amortized analysis? What is it?
Just
The name.
Define it.
it's analyzing based on the overall cases instead of
Exactly.
just case by case basis.
Instead of looking operation by operation, what's the worst case? Let's look at a sequence of operations and calculate the runtime for all of those, and then divide that by the amount of operations, and you get something smaller. So you could have something that's O of 1 in amortized, but O of n in worst case.
It's like an average, but not quite.
Exactly. It's kind of like, let's look at bigger picture instead of just every single operation in the worst case. Okay. So in amortized analysis, instead of analyzing a single operation, we'll analyze a series of operations. Let's denote a series of operations as all these different sigmas. And let's denote C of I, the price of the sigma I operation. And we're going to want to calculate the worst case. We want to calculate the worst case over all of them, not just over one, and that's going to be called amortized analysis. We're going to denote it by this C hat equals the sum of all of the prices of all the operations divided by the amount of operations. This is the definition of amortized analysis. And therefore, we can say the price of each one of these operations is this in amortized analysis. Instead of if this was n and this comes out O of 1, it doesn't matter. We have one really heavy price. We'll see a bunch of examples. There are 3 different ways of analyzing it. You saw in the lecture. There's the aggregation method. It's called the bank method. I don't know how you say it. What? Accounting method, and the potential method. Okay, so we'll go through them one by one with examples, and it'll become slowly clearer and clearer what we're doing. So in the aggregation method, we want to just go by the definition of amortized analysis, which is the sum the price of all operations divided by the amount of operations. So let's take an example. Incrementing a binary counter, right? So each operation, all we can do is just increase this digit by 1. So let's just take an example. We'll increase it by 1, we'll increase it by 1 again, and it flips, but the next bit becomes 1. So on and so forth. For all of these different operations, so we only have one operation. It's just incrementing it by 1. We can't decrement, we can't reset, we can't do anything. All we can do is increment it, right? It just increments it. Now, notice that if all of these were 1s and we increment it, we have a very pricey operation because we'll have to switch every single bit, right? We have to switch every bit. That's going to be one very heavy operation, but we'll show that it doesn't happen very often. So if we take a sequence of operations and calculate total for them and divide that by the amount of operations, we'll get O of 1. Okay, even though technically it could be a huge operation, worst case. All right, so first, what's the price of that increment operation? In the worst case, O of k, which is the length of the counter, right? Because we have to change every single bit. It's all 1s except for the last one, or it's all 1s. And we increment it, it causes a cascading effect, and then all of them will have to change all of them, which will cost us OK. Now, what's the amortized analysis of this? We have to calculate first the total amount for a sequence of operations. Okay, so let's look at the sequence of operations, of incrementing operations. Note that this bit, the first bit, switches every single operation, right? It goes 1, then 0, then 1, then 0, then 1, then 0, then 1, then 0, right? Look at just this bit, it's 1, then 0, then 1, then 0, then 1, then 0. It always changes 1 and 0. So it changes every single increment. What about this bit? How many?
Two.
Every 2. Yeah, to the power of 0 of 1. Yeah, to the power of 1. So this one will change every 2. And what about this bit? Every 4. This one? Every 8. 16, so on and so forth. So we found a pattern, okay?
7.
So therefore, the ith bit changes every e to the power of I operation. So let's use this information to calculate for a sequence of operations what the total price of all of them is. So the total of every single, this is the operation. C1 is the first operation, C2 is the second operation. So for a sequence of n operations, here it's just increments. The total price is just the sum of all the separate prices. Now that equals to n, because we're doing n times. K is the amount of bits, and 2 to the power of j is just that we're now, instead of counting the price of each operation, we're going to count how many times each bit switched over the n operations. Okay, so these are the times, each digit, each bit. So we have the first bit changes every 1 operation. So therefore it's n divided by 2 to the power of 0, which is 1, which is just n. The first bit does n switches. The second bit, when j equals 1, does n divided by 2 switches for n increments, right? That's what we're calculating. For n increments, we have n divided by 2 switches for the second one, and n divided by 4 for the third one, n divided by 8 for the next one. That's what this is. This is smaller than n. We just took it out from j until infinity instead of stopping at k. 1 divided by 2 to the power of j, which is just a series that goes into infinity but gets smaller, and which we know already is 2 times n. Right? We did that a couple of times. We even used the binary trick to actually calculate this series. So therefore, now we know if the price for all of these operations, for n operations, equals 2 times, not equals, sorry, is less than 2 times n. Okay? So now we take the price, the amortized price for each operation. We take the total amount of operations divided by the total cost of all the operations divided by the amount of operations. So the cost is at most 2 of n, and the amount of operations is n. Therefore, the price in amortized is 2 for every single operation, which is O of 1. Okay? So therefore, we just proved with the aggregation method that it is O of 1 in amortized. Okay, questions on this?
I don't think less than is correct here, because even if it's not much bigger, it is bigger, no? Okay, like,
What do you mean, that this is bigger than this?
I mean, yes, but some small amount.
Yeah, it's very tiny. It's very, very tiny. You can do like almost equivalent, right? Like you do like the almost equivalent. Also, you can just look at it. This is we stopped at the kth bit, and technically, if we increment like that one twice, it just starts from the beginning. But then we can just keep on counting the bits, right? This is like if we had unlimited space. This is if we have k bits. It's like very you're right. It's very similar. That's why we're gonna do something a little bit more exact. We said the counting method. What?
Bank.
Bank. Yeah, bank is much better. In this method, we're gonna refer to every operation. We're gonna give it a different price than it actually has. So basically, we're gonna pay for things ahead of time. Before, exactly. And then we're gonna have basically a bank account, a balance that we can use for heavy operations. So for all the cheap operations that only take 1 action, we'll give it more than 1. Then we'll use all that stored up operations. We'll use it later. Okay, so like we said, if it's a low price, if it's a low cost for the operation, then we'll just add a little bit more and save it for later. And then for the high cost, we'll use all that stored up let's call it
Debt.
bank balance debt that we have. So let's do the same exact example. Remember our bit increment. Now, what's the cost of a increment? So let's pay for every increment. Let's pay two, let's call it shekels. Okay, for 2 shekels, which is basically just cost of operation. So if we're only increasing the first bit, then we have an extra shekel, right? Because we only increase the first bit, we have an extra shekel we can change, save for later. Note that for every operation, we turn on a certain amount of bits and turn off a certain amount of bits. We turn on, turn them to ones. Turn off is turning it to 0, right? So therefore, each shekel that we have for increasing a bit, 1 shekel will be for igniting a bit, and the other shekel will stay with that bit. And the second we want to turn it off, we're just gonna have a shekel that we already saved up. So let's see it. Let's see it in an example. We turn the first one, we increment the first one, we pay 1 shekel for turning it, and we save 1 shekel, we put it next to it, save 1 shekel for future use. Now, when we want to increment it again, we turn this one off, and we're going to use this shekel, and then we're going to light this bit. Okay?
I don't understand.
We need 2 shekel. Okay.
I don't understand what you're trying to like. What the whole idea is trying to explain here. You are saying that you have 1 shekel which you have to pay later, or is it 1 shekel that you get?
It's 1 shekel that we pay ahead of time. For the first operation, it's very cheap, right? We just increment it, the first one. It cost us 1.
Okay.
Let's pay 2 right now up front. And then we'll have 1 for later because we only used 1 of them.
Okay.
So we have 1 for later. Okay?
Okay.
And now when we increment it again, we'll always pay for the bit that we turn on, that we switch to 1. We'll pay that 1. Okay? And we'll keep a shekel here. And then if we want to turn some sort of 1 to 0, we just use the shekel that's above it that we use to turn it on.
Sure.
Okay, so let's say for this example, now we want to increment it again. So we pay 2 shekels again, right? We increment this one, which turns it to 0. When we turn it to 0, we use the shekel from earlier, from the previous one. And we turn this one on using one of the shekels that we use for this operation, and then we save 1 of the shekels for later. So for every single one that we have, we'll have a shekel, which is basically saved up, stored up operations. So therefore, no matter what the operation is, I'm always paying 2 shekel. No matter if I have 1s across all of this, for every 1, I know that I have a shekel above it. So therefore, even if I have a really heavy, expensive operation, in order to turn off bits, I know I already paid for it ahead of time. I already paid for it. So all I have to do is turn on that 1 bit at the end. So let's see, let's continue. So now if I were to increment it again, what's going to happen? I'm going to increment it, pay 1 shekel. And because I turn it to 1, I'm going to save a shekel for turning that 1 off later. And now when I want to do a heavier operation, right? What I'm doing is I'm turning this off, which I already paid for ahead of time. And I'm turning this one on, which I'm paying 2 shekel, 1 for turning it on and another shekel for later, for when I want to turn it off. So you're paying the operations ahead of time, right? And so on and so forth. Okay? Thomas, it's really confused.
This is the most Jewish explanation I've seen to anything we've done so far.
It's the best it's Bailey's method. This is the best method. The bank one, yeah.
You use it every time. Every question you're gonna use this one,
The bank is the best and most important method.
except for the ones you can't.
Just wait till I get to potential. It's even more confusing. Okay.
Okay.
Well, Thomas, definitely watch the lecture.
No, I understand. Yeah, I understand what you mean. I just like want to.
2 shekels, because you have to pay another one for like.
No,
It was 2 shekels.
like
We paid 2
2
shekels on each operation.
Okay, it says for each one.
For each bit that's on, it's a one. We have 1 shekel that we already paid for.
Still pay.
Exactly.
And we used one of them to increment it.
Exactly.
Right?
So it's a very it's idea that appears in a lot of questions because you can pay for the cheap operations ahead of time if you know, let's say in a stack. You did this in the lecture where you I think you did
We
or
didn't
2
do
stacks
it.
or
No.
you did it with
So,
dynamic or with pop. Oh yeah, with the
Pop
no, with the multi
and
pop.
multi.
Yeah, where the multi pop is really expensive because you have to like take them all out. But if you insert 2 shekels, then the multi pop will be free because you already paid for all of the elements to take them out. Okay, so I promised a
About
lot.
the, like exponential reduction here again,
No.
or that I always have enough coins.
No,
Words enough.
your words are enough in this case.
Okay.
Technically,
only
for an
one.
actual proof, but I think we just don't expect that level in this course.
If you would want it, you would ask me in the question.
Yeah.
Prove it.
Yeah,
Okay.
yeah. For almost all questions, this is enough. You've also done a lot of tests. You see that like usually they just do
Yeah,
something
but
like this.
you can't put one.
Ah.
Like some people do write it, some don't.
Mm.
This takes down, this doesn't. Like there is
Got
no formal like answers to tests, so you never know.
Got it. Okay. So potential method. It's the mathematical basis for the accounting method. Right? Because the accounting method we're basically saving for later. And this is the mathematical representation of that. Okay, so we'll see it. And hopefully it'll become a little bit clearer. It's inspired by the physics idea of potential energy. If you learn physics, you know that if you have something on a building, it has potential energy if you drop it. It's the same idea here that we pay for things ahead of time, like for like the accounting, and then it has this potential energy that we saved up. Instead of saving coins, this is just having that total amount of energy for each operation, that potential energy, and then changing that potential energy is whether we saved or didn't save it. Okay, so the idea of this is we'll just define potential for every single operation that we do. So for every operation, the potential can change. If the potential increase, that means we saved up, right? The potential increased, so we have more energy that we can use later. If the potential decreased, that means we use that potential for paying for an expensive operation. Okay? So the idea is you go up stairs, which is hard and difficult. You go up more stairs every time. And when you need to do a very expensive operation, you just go down the slide and it's free. So every step you go up either 1 step or 2. For every couple operations, once in a while you pay for an expensive operation with the potential. Let's do the mathematical denoting and definitions of the potential method. Okay.
That's one sigma. That's always the whole point.
Okay, so first denote by di the situation in our data structure after the ith operation. Okay, so we have n operations, so d2 would be the status of our data structure after the second operation. The starting is d0. So let's look at a potential function, and which basically takes each situation of the ith operation and sends it to a real number. Okay, so that's our potential. And then the actual amortized analysis price would be the actual price plus the potential that we have now minus the potential we had beforehand. So if, let's say, we pay a really expensive there's a really expensive operation. We use a lot of potential. So if we use a lot of potential, this is going to be a lot less, right? Sorry, wait, no, this is going to be a lot less because we used in this operation a lot of potential. We used it up. So this is going to be more than this, and therefore we'll have negative to pay for that really expensive operation. If though we have we increased our potential, we're saving up potential. That means that this is more than this. It's a very cheap operation, so we can save up the potential. Because this is more than this, we'll have plus a positive number that we're saving up for later. We always take the difference of the previous potential and this potential.
Potential means potential to have to do a lot of work, or is it like
It's potential of what I have saved up. Like in the accounting, it's like what I have saved up. So here the potential energy is how much energy I could use to go down the slide. You can think about it as like sort of like a credit score. You pay for things and then you only pay at the end of the month. You don't necessarily have to pay, right? So this is what you pay. This is the potential of at the end of the month. And this is the potential of last month. So this is our credit score now. And this is how much we owe now. This is how much we owed last month.
so the key to everything is credit fraud?
Exactly. Exactly. Fraud is the answer to everything. All right,
Now,
let's
so I think I understood that. So it's better when we have less potential or we have more potential?
If we have more potential, it's a better situation. Right? If we have more potential, we can use it later.
Okay.
If we have less potential, we don't have a lot saved up.
I have too much to say for sure.
Okay. So this is our actual cost, and this is the difference between potential.
Mhm.
Like if we are on a building and we move one floor up, we increase our potential energy. If we move down a floor, we use some of our potential energy. There's a lot of examples. This takes a while to get. Now, before you freak out, this isn't so complicated. This is the sum of all the operations in amortized.
Mhm.
Okay, which equals, this is by definition. What do we say each amortized operation equals? It equals the actual operation plus the difference in potentials. All right, so we just separated these into two different sigmas. So we have the actual price of the operations plus the difference between the potentials. Now, you can tell that this is a telescopic series,
Mhm.
right? Because for everyone, we subtract the previous one. So therefore, it'll be equal the last element minus the first element. Okay, that's all that it's saying here. So for a series of operations, you take the actual price of all those operations plus the potential at the end minus the potential in the beginning. Okay?
Graphic has the same place. How would you do that?
For our potential function, we need certain qualities, certain for example, not for example, we assume, but we need to define it well. If you don't define it well, this doesn't happen. Okay, you define the potential function. We'll see an example of that soon. You have to define it according to something. And you want that the potential of the first state is going to be zero. You start with zero potential energy. And you want that the potential of every single state is greater or equal to zero. You don't want to ever go into minus. Okay? So those are two requirements for our potential function. Okay. Bear with me. For our binary incrementation, we can define for every DI, for every phase, for every operation, the potential of that same state equals the number of bits that are ones. Right? If you remember from the counting method, we had a coin for every one, right? So this is just the potential is going to be the amount of ones, right? If you just count the coins and count the amount of ones, it's the same thing. So that's going to be our potential energy. And let's assume that increment, we turn off t different bits. And we turn on 1 bit, right? Because we're only in every operation, we're going to turn on at most 1 bit, and we can turn off a lot of bits, but we're turning on at most 1 bit. So therefore, the actual cost is going to be t plus 1, because we turn off t bits and turn on 1 bit.
This is like kind of like the worst case of like if we turn on one and we have to turn off all the other ones. So it's kind of
Exactly. This is kind of like a worst case that like this would be the actual price of the operation, which is it could be something to do with K or N. Right? So this is kind of like a bad case. And now let's note that if before the operation we had X bits on, x bits that are ones, then our potential beforehand, right? Our potential in the state beforehand, before we turned off t bits, is x, right? Because we had x bits on. Therefore, by our definition, it equals to x. And also, we can note that the potential now, after we turned off t bits, now we have x minus t bits that we turned off, plus 1 that we turned on.
This one I did.
This one you didn't understand. So our potential now is the total amount of bits that are ones, right?
Yes.
So we know from the state beforehand there are x bits that were on.
I understand.
And now we turn off t bits and turn 1 on. Okay, so our potential is now, the potential in the state of I is now equal to, and therefore our price, our amortized analysis price for CI equals by definition to this, right? That's by definition, which equals, now we have the exact what each one equals. So if we just plug in for this, we have x, and for this we have x minus t plus 1. We just get this, which the x cancels each other out, t's cancel each other out, we get 2. So for every single operation, the amortized analysis price is going to be equal to 2, which is kind of like what we showed in the accounting.
Yes, so when we did the accounting, every place we had a 1, we had a section, right?
Exactly.
And this is the x actually, this is like the amount of stuff we have. And then when we did an increment, we like paid all this stuff that we had, but
Exactly.
we also like gained 1 more because we turned 1 off. So this is like,
Exactly.
so this
Exactly. This is just, instead of counting coins, now we're just counting the potential. Not exactly where, we don't care where we put the coins, but it's just counting the amount of coins.
yeah, but it's kind of equivalent. Like
It's
we're counting
equivalent.
the potential on counting how many coins do I have
Exactly.
before it and after it.
That's what we said in the beginning. This is the mathematical basis for
Yeah, but
accounting.
I'm trying to connect it. But you
Okay,
can-
so yeah, this is the mathematical basis of the first one. This is more formal. This is easier to prove. This is already more solid proof. Then the accounting was like, here, let's look at coins. Yes, Sam.
Why did we drop the sum, the sigma?
Why did we drop the sigma? Oh, for all of the different operations? Because in this method, in the first method, the aggregation method, we summed for all the operations and we divided by the amount of operations.
Yeah.
That's just by definition of amortized. But here we define a potential function, and we show that for every single state, the amortized price is always equal to. So we don't need to show for like a series of operations, because we showed for every single operation within that series.
Yeah, you've lost me there.
I lost you there.
I don't worry, he lost me like half an hour.
So the price for is, before we did the first series of operations, divided by n, the amount of operations.
Yeah, no, I understand the.
Yeah. So here we define this potential function, and it basically saves us from summing over all the different operations, and we can just calculate for like, let CI be some sort of operation. Let I be one of the operations that we do, and CI is its cost. And we show that the amortized cost for that specific operation is 2. So because we did let some sort of CI, we just proved it for every single CI. That the amortized cost by definition that we defined is equal to 2.
Right, okay, so if we were to sum it, we'd sum until n, so it would be 2, and then we divide it by n.
Exactly, it's the same thing. You don't have to. We just proved it for anyways.
It's essentially by.
Exactly. This is a different
by
definition.
assuming it, by proving it for all, it basically cancels out the need to.
Exactly. And also you can think of it like the aggregation method. We had to sum up all of them and divide, right? But here, that's the definition of the cost, amortized cost of CI. It's just sum up all of them, divide by n. That's the actual definition. But here we defined a different definition using the potential functions. So it's 2 definitions to calculate the same thing. You can choose whichever one you want. Okay.
Why did we care on the slide beforehand about
Hmm?
why did we care on the slide before about doing the telescopic sum and finding that general formula?
Doing the what? The
If
telescopic.
you go 2 slides before,
Oh yeah. It helps in certain cases.
because in some
In certain cases, you know the potential at the end. You know the potential. What?
in some cases, not every operation is the same. So to say.
In some cases, but usually we're just going to do it this way, just by the definitions. But sometimes you can do it that like the series is equal to the actual cost minus the potential at the beginning plus the potential at the end. Sorry, the other way around. You can use that definition too. It's just a bunch of definitions for the same thing. Whichever one's more convenient for that specific problem, you can use. Okay, so I guess I showed this for quite a while. So I guess we're going to do this. And then next class, we'll go over, there's a couple more questions at the end. We didn't get through all of them. Let's just, this one's a really good one from a test last year. Really cool question. All right, let's do it. So you need to suggest data structure of type that's similar to a stack that supports the following operations. Init k, which is just initializing it with for natural number k. Push x is for a number x within the range of k. That's why we have the init k, because it's probably going to be similar to like count sort or something, where you have the k like array, like a size of k array, and then each number has to be within the range of k, between 0 and k that we put in. And so that's going to be pushing it into the head of the stack. Pop is printing and returning and taking out of the stack the element in the head of the stack. And delete is actually deleting all of the different appearances of that element.
Is it from the first one or the second one? First one.
First one.
This is the only
So-
question I got in the test, and I got
It's
that
a
one.
great question. It's really cool.
It's the only one. It was my only hope.
So
All right, so try and take a minute to think yourself, and then I have to go through it quickly. So I don't have time to like talk about it.
I think that you make a stack and then you make k buckets, and each I don't know, two stacks and k buckets. So you every time you input a number, you just I don't know that how much time should the delete take?
Well, here they just say do it in the best time possible. I think that's what it says.
Yes.
No.
Oh,
Here.
They say do it.
Oh, wait, here. Oh, wait, no, never mind. Usually, I think on the test, they also said just do it in the best time possible. You have
They
to
don't even tell
understand.
you what the best time possible
Don't
is.
even tell you what it is.
no.
Sure.
Yeah.
So
You have to figure it out.
They did limit the amount of space. I do remember that. They said the knit this. They didn't. They said do the best time, but they limited.
They limit it in O of
This
K.
they wrote.
This they wrote?
Yes, this they wrote.
No, this is time
The
though.
last one. The last one. These
Oh,
ones
this
they
they
wrote,
wrote.
and this was like the key to like solve
Yeah,
it
okay.
also.
So
it's kind
now
of that.
let's assume I'm going to give you guys a hint. These are the running times of each operation. In
How are you
this
supposed
case.
to just know what?
You do a lot of questions, but
Then you hope for the best.
in general, you just try and you think of a couple ideas, and you try and always improve your idea.
So
Yeah.
okay, so this
So
is
now we have
important.
this amount of space. This is basically the key.
This is very important because you can have buckets that like have infinite size. So you have to like
Yeah, you can have
you
your own
need
infinite size.
an array of size k, which is the amount of elements, and then you you have pointers there to the last element. I think. Yeah, the problem is that delete takes off one. That's crazy. Okay.
Delete takes the whole
Okay.
one. Okay, so
Use up.
I'm just gonna first off, it's similar to a stack, right? So we need a stack. It's gonna be the size of O of n, correct? So we already have the space O of n. Now what's the space O of k? That's why it's a little bit of
It's
the
an auxiliary array of size k.
exactly. It's auxiliary array size of k. That's gonna be our O of k. So it's from 0 to k. Now, how does this help us? So we're going to try and do an amortized analysis because, right, push and pop are both O of 1 and amortized. So the idea for this one is use what's called, like what I call in other methods, I call a blacklist. So instead of basically deleting every single appearance of that in the stack, we're just gonna have a bit that says, let's say the third element, if this is, let's say, false, then we know that the third is deleted. All the threes are deleted. Okay? It's also important to note that delete, I think it says here, delete, once we delete it, you can't enter it anymore. Right? You can't enter it anymore. It's a very also important clue that once you delete it, you can't enter it anymore. So now if we have some appearances of 3 here in the stack, let's say we have 2 here. If I do now pop, for every element, I'm going to check in our auxiliary array whether or not it's already deleted. So here I check for 3 and I check it's deleted. So I'm not going to return it and I'm going to keep on checking 3, it's deleted. Pop, 3, it's deleted. 2, if 2 is not deleted, then I can actually return it and then I'll return 2. Okay, so let's just see that. Sorry, it's a lot of words. So these are 2 data structures, and this is a Boolean array. They called it D.
But then couldn't pop end up taking?
Yes, pop could take a lot, and that's why we use amortized analysis. Ah, come
I was
on.
going to say, my calculations were almost done.
Okay, do you mind if I take like 2 more minutes to explain the answer?
Sure.
Okay, so I'll just explain it. Like Sammy, it's a very, very good observation that each pop could take a really, really, really long time because I could have to pop out all the elements of the stack. So it could be like O of n, which is really not good. But that's why we have amortized analysis. Because for every push, we're going to save another. We're going to use the bank because that's really the method that's simplest. We can use a bank, and for every single element that we put in, so we put in, first let's initialize everything to true, and then we, if we insert something, we keep a shekel, right? That's the bank method. Let's say we insert 3, keep a shekel, 2, keep a shekel, 3, keep a shekel, 3, keep a shekel, and 1, keep a shekel. So now let's say we delete 3, right? So 3 is deleted, but 1 isn't. So pop, we first get 1, right? Just took us 1, which we already paid for beforehand. And then 3, even though you're right, we could have to do a whole lot of 3s. Let's say there's a lot more 3s that we entered. So for each push, we pay 2. But for each pop, we already paid for it in the push, right? Each element can only get, and every element inserted can only get popped 1 time. So therefore, if we have a long series of pops, then we pay for it with our shekels ahead of time, right? And then once we get to an element that we actually can return that's not blacklisted, we return it. And therefore, in amortized, it's O of 1, but in really in worst case, it's O of n.
But then how are you doing this?
What? You could. Oh, so here it's. I'll show you the question, but it says once you delete an element, you can assume it's not pushed. You can't push it.
How do you do delete in O1? Because you still have to go through the entire thing.
Delete is O of 1, so you don't actually delete it physically from the stack. It's still there, right? All the 3s were still here.
But then you still have to go through the stack and like.
No, you don't have to do. No, I'm not going to do anything. All that I'm going to do is, let's say I delete the element 2. All I do is turn this to false. That's O of 1. That's all. I don't touch this.
But if they're n2s, then you have to go n times and.
But that's the thing, is I'm not changing the stack. If there's 2s here, I don't actually go through the stack and delete it. I don't actually delete it. The only time where I like delete it is when I do pop. Because when I do pop, then I check if it's deleted or not.
Oh wait, that's a separate array. Oh,
yes.
Okay, that's really cool.
All right. So it's a really cool idea. Blacklisting. Okay, first, this is important. It's just I explained the rest of it like verbally, but let's just analyze the complexity. First, obviously the space is n plus k because we have a stack of size n and a array size of k, and the runtime of initialize and delete are both O of k and O of 1. So initialize is O of ky because we want to initialize this whole thing to true. Deletion is O of 1 because, like we said, you just change the element to false that just index, which is just O of 1. And now let's just do push and pop together. Let's analyze them together with amortized analysis. Let's use the bank theorem. Whenever we push an element, we'll pay 2 for it. We'll pay 1 for now for inserting it, and 1 for later. So save a shekel for later for when we have to remove it. And then because, and this is, you do have to explain your answer, because every appearance of x that we inserted into the stack can only be removed at most one time, because once you remove it, it's gone, right? You don't have to remove it again afterwards. So because of that, we already paid for it ahead of time, and therefore both of them are O of 1 in amortized analysis. Now this we're going to do at the start of next recitation. It's really cool stuff. It's a little bit easier and cooler questions to build off of each other. But for now, there was actually a second part to this question. If you want to listen, you're welcome to listen. If not, you're welcome to not. But the second part of this question was now, right, once we delete something, we can't insert it anymore. Right? You can't physically insert it anymore because you can't pop it afterwards. It wouldn't work the same. So the second part is turn this answer. Now give me a different answer where you can actually insert a deleted item again. So the trick for that is, and this is just verbally, I'm going to do it really quickly, instead of doing true and false, instead you have a number here. Instead of true and false, you have a number, and that number indicates at what time was it deleted. Okay, so let's say if we delete, we keep a counter, which is just every operation we increment it by 1, right? And then whenever we push an item, we save the item and the time that it was pushed. Let's say it was pushed at time 5. Right now at time 7. If I deleted the item, let's say this, we pushed it in at time 8. Right? If I deleted 3 at time 7, then I insert 7 to it instead of a true or false. Now I have a number. And now when I pop it, I don't only check if it's true or false. I have to check the second element, the time that I inserted it, if it's before or after this, right? So now we're at time, let's say 9, and we pop, right? So let's say we don't have all of these, we pop. So therefore, we deleted 3 at time 7. Therefore, when we pop this 3, it's okay. We inserted it after we deleted it. But if we pop again, if we pop this 3, it's already not valid because we deleted it, because the time that we deleted it, it was after we already inserted it. So that's the answer for the second part. Obviously, you still have to do it formally and explain. But that's a general idea. It's just the blacklist with true or false, and then blacklist with a timestamp. Okay, so we're done for today. That was the hardest question. We took it from last year. It was the hardest question. The rest of the questions are much easier. We just ran out of time. We'll do them next time. You'll see it's a lot simpler. Okay. Skip questions. Oh no. Oh no.
It's only after the
Oh, after the thing disconnected. Okay.